Hello, in this video we will be looking at the different types of boundary conditions that we can apply in fluid dynamics and give some examples of such boundary conditions. So to look at boundary conditions we need to make several cases, and the first case that I'm going to go over is the case of solid boundaries. So in the case of solid boundaries, for instance, I've got a fluid flowing down a pipe, which could be an example, and I've got fluid inside this pipe or channel. I'm going to be referring to these two boundaries here and there. So at these boundaries we need to impose effectively one condition, and this condition is a condition on the velocity. And it is that the velocity of the fluid at the wall has to be equal to the velocity of the wall. And this is in a vectorial condition. So U in the fluid has to be equal to the velocity of the wall. And this boundary condition is due to the friction there is between fluid particles and the wall. The wall is moving at a certain velocity, so the particle adjacent to it have to move at the same velocity. As a consequence, this is a boundary condition that is called a no-slip boundary condition. If we really want to be exhaustive on this, we should be saying that we should also add a condition on the stresses within at the boundary condition between the fluid and the wall. But this is a condition that is automatically satisfied, so we don't need to remember it. Effectively, it's due to Newton's third law. Newton's third law. It states that whatever stress is applied by the fluid onto the wall, an exactly opposite stress is applied by the wall onto the fluid. And of course this condition is automatically satisfied. So we don't have to do anything about it. So this is our first case. So remember that whenever you have solid boundaries, like these ones for instance, you have to impose a no-slip boundary condition most of the time. And that no-slip boundary condition is essentially saying that the velocity of the fluid at the wall is equal to the velocity of the wall. The second case that we'll be looking at is the case of free surfaces. So for instance, I've got a fluid that is flowing on top of a surface, and here there's an interface between that fluid and air, for instance. So I will be looking here at this boundary. In this case is a little bit more complicated. We need to think about a bit more into the detail of the physics of these fluids. But particularly the first boundary condition that we need to think about is what's called the dynamic boundary condition. And this dynamic boundary condition essentially says that at this interface, the stress coming from the fluid side has to be equal to the stress coming from the air side, or less viscous fluid. So that essentially tells us that the stress from the fluid, so this is the normal direction, this is the stress, right, times the stress tensor, has to be equal to the stress exerted onto the surface by the air or the less viscous fluid that's on top. And the only stress that this less viscous fluid is imposing on the surface is due to the atmospheric pressure, for instance, in that case. and that's going to be minus the atmospheric pressure on the normal vector. Okay, so that will be that condition. So this is the stress due to the fluid on the interface, and this is the stress imposed by the air onto the interface. And so we can express what the stress tensor is to write down this boundary condition in more detail and say that this is going to be minus the pressure in the fluid on the normal direction plus n dot sigma, which is the viscous stress tensor. I've just here explicited what the total stress tensor is, and on the right hand side I still got P atmospheric carried by the normal vector. Okay, so these are our this is our boundary condition. I can go a little bit further and you know, project this, particularly because I see that the atmospheric pressure is carried by the normal direction. I can project these equations further onto the normal direction and the tangential direction, and when I do this I get essentially two conditions. One on the normal direction, n dot n is 1, so I'm going to have minus p. Here I'm going to project this onto the normal direction, so I'm getting a n dot sigma dot n term, and on the right hand side I'm just getting minus P atmospheric. So this is my projection of this boundary condition onto the normal direction, and if I project it onto the tangential direction, n dot the tangential direction, well, these two vectors are orthogonal, so I get 0 coming from here. I'm going to have n dot sigma dot, and my tangential direction, I'm going to call this vector t, okay, so that's my tangential unit vector. And on the right hand side, I'm getting 0 as well. So this boundary condition gives me a boundary condition for the pressure or the stress tensor, the normal stress, and it also gives me a boundary condition for the tangential stress here. Okay, so for instance, we can look at an example here. So let's take the example of a 2D surface with normal EZ and tangential, I'll call it tangential EX. So we're looking at the flow in the X direction and Z direction. This is going to be U, and this is going to be the velocity W. So if I look at this, then my system, just writing down, expliciting these in terms of this new writing, I'm getting that minus P, this is the pressure in the fluid, okay, plus n dot sigma dot n, so that is going to be the normal being EZ, that's going to be sigma ZZ, and the right hand side remains minus P atmospheric. And the second condition here, n dot sigma dot t, that's going to be sigma, the normal is Z, so Zx equals 0. That gives us this. So I can explicit these stresses a little bit further in terms of the velocity. And if I do this, what I get is minus the pressure plus, so this is the normal stresses, so that's mu dW by dZ. That's equal to minus the atmospheric pressure. And this is the tangential stress on X and Z, so that's mu times du over dz plus dw over dx equals 0. And that gives me my boundary conditions for this example, okay? So this is only one part of the problem, okay? This is only one boundary condition. This is called a dynamic boundary condition. There is another boundary condition that we need to impose in the case of free surfaces, and that extra boundary condition is called the kinematic boundary condition. And this kinematic boundary condition, the aim of this boundary condition is to track the interface, because this interface can move. So let's assume that we have a surface position which is defined by f, which I'll explicit this in 2 dimensions. So that's going to be x, z, and it's a function of time. And I'm going to say that this function f is a height, which depends on x and t, minus z, and that this is equal to 0. So this is the definition of the position of my surface. F equals 0, right? And f is h minus z, or z equals h of z and t. So z will be, h is the height of fluid. And this kinematic boundary condition translates the fact that particles that are on the surface remain on the surface. Okay? And this mathematically translates into writing that the Lagrangian derivative of f with respect to time equals 0. And I can also write that in a more in a verbose manner by saying that this is df over dt plus u dot grad f, that is equal to 0. Okay? All right. So and I can replace f in this expression by h of z and t minus h of x and t minus z, and if I do this, what I get is dh by dt plus u dot grad f, which turns into plus u dh over dx. And I've got minus z here, so I am writing equals w. Okay. So this is this kinematic boundary condition. So there are some interesting remarks from it, particularly if the surface is steady. What we get, so that means that df dt equals 0. What we get is that u dot n, the normal vector, equals 0. And this is the case because the grad of f is the normal vector. Okay? The gradient of that function tells you the normal direction. And this is an interesting remark because if the surface is steady, this means that there is no normal velocity to the surface. So in a sense, this would translate directly into a boundary condition for the velocity like the one we had in the case of solid boundaries. Okay? It's a sort of impenetrability boundary condition. Lastly, and there are many variants of these boundary conditions that can be used. These are the most commonly used. They're all right to make models of fluids. I'll just introduce one last boundary condition. So it's the boundary condition at the interface between two immiscible fluids. So let's say, for instance, you have a fluid that is in a sort of channel like this, and it's constituted of two fluids, right? So there's a fluid 1 here, and there's a fluid 2 here. Okay, and these are immiscible, so they won't mix. So the boundary condition that I'm looking at is the boundary condition at this interface. Well, it's very simple, in fact, because what is happening at this interface is that we need a condition for the velocity, and the condition for the velocity is that the velocity of fluid 1 at the interface, so the top fluid, has to be equal to the velocity of fluid 2. And the second boundary condition that I need here is a boundary condition on the stresses. And it's just a continuity of the stresses at this interface. That is to say that the stress in the fluid 1, so I'm going to write sub 1 to indicate fluid 1, has to be equal to the stress at the interface that is created by fluid number 2. And that's it. That's as simple as this. So I've just detailed here 3 cases. These are very common cases. These are a bit more obscure cases. And the boundary conditions that I've described here, they are boundary conditions that are common, but they are not the only boundary conditions that one can impose onto a problem, into fluid dynamics problem. This concludes this video on boundary conditions of fluid dynamics.